Today, we are diving into something I wanted to create for a long time. A practical playbook for reliable finite element analysis. This is a complete guide that blends essential theory with hands-on best practices. Not to help you push buttons, but to help you think like an experienced analyst. Hi, I'm Dr. Iman. Welcome to FEA Done Right series at MechCADemy. Many students have asked me to personally guide them through FEA, but I cannot teach everyone one-on-one. So I made this series to give you the same step-by-step guidance I would share if we were sitting together. We'll cover theory, but I'll keep it focused and manageable, just enough to help you make better modeling decisions. And I'll keep it practical. You'll learn what to do, what to avoid, and how to think. If you want to go deeper later, think of this series as your first stepping stone towards advanced learning. So, whether you're a student like in mechanical, civil, structural, or aerospace engineering, or you're already an engineer using FEA, you'll find ideas here that strengthen your foundation and sharpen your skills. This is one of the most important series I made for MechCADemy, and I'm really excited to finally share it with you. If it helps you, please support the channel, subscribe, like the video, share your thoughts in the comments, and pass it along to someone who could benefit. And feel free to connect with me on LinkedIn. I'd love to hear your experiences and continue the conversation. Let's learn how to think better, model smarter, and run FEA the way it's truly meant to be done. For this intro to the series, first let me show you the big picture of FEA. What does a typical finite element workflow actually look like? In most projects, the process falls into four main stages: simplify, model, solve, and interpret. We must remember that our theoretical foundation and engineering intuition and judgment are essential tools in these stages. Now let's briefly cover each stage. First, we simplify the real-world problem. This is the first part of pre-processing. Real engineering systems are usually too complex to simulate directly. So, using right justifications, we simplify the geometry into something suitable for analysis. That may mean removing tiny fillets, idealizing fasteners, or replacing a complex assembly with a representative substructure. Once the geometry is manageable, we move to modeling. This is still pre-processing, but now we prepare the problem for computation in the actual FEA interface. We mesh the geometry, assign material properties, apply loads and constraints, define contacts between parts, and set the solver settings. In this stage, we again use our engineering judgment to utilize various assumptions and simplifications. We also make modeling choices for boundary conditions, material behavior, and contact assumptions. So the problems become physically sound and numerically solvable. After the model is set, we enter the solve stage. This is where the software uses numerical methods to compute the unknowns. In linear statics, you can think of it as F equals K times A, where K is the total stiffness matrix, A is the displacement vector that we are looking for, and F is the known external force vector. This stage is often the most demanding in CPU or GPU and memory, especially for nonlinear, dynamics, or very large models. Finally, we interpret the results. Another name for it is post-processing. This is where engineering judgment matters a lot. We visualize the stresses, displacement, temperature, or other field. But the key step is this: we verify and validate. If something looks off, we explain it, and if necessary, we improve the model. Therefore, very often, this stage loops back to the pre-processing until we trust the result. So, that's the big picture. A short one though. Now let's begin the series with section 1. In section 1, we focus on what you must do before you even make the model in the software. See you in section 1.